Hello, everybody. So my name is Christoph Sorger. I'm an algebraic geometer, but my current activity is being the Secretary General of the IMU. And as Ulrike explained us this morning, every year we have a meeting of the Executive Committee, in general in March. And we try to go to the places where our members of the Executive Committee are working. And this is why we were in Sydney last year with Nandini Yoshi. And this is why we are in Cambridge this year. So I must say this was a very lucky choice for the timing, because the weather is nice, and despite of what Wendelin tried to sell us, that's not necessarily every day like this here. And we were also lucky, and this is second lucky timing we have, that we have two interesting programs running just this year and just now, especially the Modern History in Mathematics program and the program on homotopy. So if you look at the title, there are some relations, at least from the topology part maybe. But the idea is that we have three 20-minute talks, and that we have half an hour of question and answers later. This is why we have put 4 chairs. So the 3 speakers will just give their 20 minutes talks in a row. Please don't ask questions directly after the talks. Keep them in mind, and you can ask them when we do the question and answers session. So it's my pleasure to introduce the 3 speakers at the same time, because we just go one after the other. This will be smoother. Let me start with the third one. So when I first read the title Modern History in Mathematics, then if you're not a historian, you can make an easy mistake thinking about modern history being modern history in the sense of the 17th, 18th century. But this is in contradiction with the title of his talk, which is about modern approaches of history. So, and about the 20th century. This is what we hear at the third talk. Second talk, by Volker Remmert. I know him from Mainz because one of my main collaborators, Manfred Lehn, is in Mainz, and I'm very often there. And I was lucky to meet Volker there. Second speaker will be Niccolo. Oh, now I must be very careful with the pronunciation of your name. I tried already several times to be. You can approximate. It's Guicciardini from the Universität of Milano. Thank you. And and also here had a fast reading of the title. I was reading Digesting Isaac Newton and the Principia. But this is also an interesting program, but we are talking about digitizing. Digitizing Isaac Newton and the Principia. So I'm very interested in seeing an online version, and probably a commented online version. I hope you will explain to us a little bit more about this project. And so the third introduction is for our first speaker, June Barrow-Green. So June, I know her as, even before I knew her, I knew her about the fact that she's the current chair of the International Committee of History of Mathematics. So this is actually a joint commission. So it's shared with the Division of History of Science and Technology of the International Union of Philosophy of Science and Technology. And so you're the chair of this commission. You told me you will say a few words about it, so I will not say more than that. The IMU has some commissions and committees. We have another one, which is the International Committee of Mathematics Instruction, ICMAI called, And this one has been founded in 1908. I'm trying to show you that I have some small knowledge of dates, at least. And first president has been Felix Klein. So we are very proud of our commissions and committees, and of course also of the one of History of Science. But I met June as the curator of the archives of the IMU. So the archive is small. It has been founded by Olli Leto, but I think it's an interesting archive. There are many interesting things in this archive, and this is why we met in Berlin some time ago, when you explained me what it means to be a curator of an archive, which of course I didn't know. Okay, thank you very much, and we'll start right away with June.
Okay. Thank you very much, Christoph, and thank you all for coming. It's wonderful to see such a full room. Okay, so I'm just going to begin, as Christoph said, I have to say a quick word about the ICHM, mainly just to advertise for those of you who don't know that one of our main roles is in awarding grants for history of mathematics research and events, and giving priority to early career and disadvantaged scholars. And also this summer we have our kind of big moment that happens every 4 years, rather like the ICM. It's the ICHST, and this is where we award our May prizes, which are the kind of premier prizes in history of mathematics internationally, and the Montoucler Prize for early career scholar. So if anybody wants to know any more about the ICHM, please don't hesitate to ask, or you can look at the website, which is on the IMU website. Christoph also mentioned the fact that I'm the IMU archive curator, and I just wanted to draw attention to an article I wrote recently with the help of the archivist at the IMU, Birgit Seeliger, because there have been some recent donations to the archive of memorabilia from ICMs, and the archive is trying to gather as much as they can in terms of items and information about past ICMs, and I was really happy that as a result of this article, some Dutch mathematicians got in touch and let us know about some really important archive material about the ICM in Amsterdam in 1954, which the archive, the IMU archive didn't know about. So again, there's a plea for anybody who knows anything about past ICMs. Would absolutely love to hear from you. So, okay, enough advertising. So the wartime diary of a senior wrangler. So this is something that I found in the St. John's College archives many years ago, and I've been trying to find time to work on it. It's the diaries of a student who was at St. John's during the First World War, and it is an amazing resource in as much as it's very detailed, and he writes about 3/4 of a page of A4 for every day for a good, over the years, well, from the beginning of 1915 until the middle of 1916, and then a bit more later on. And for historians, the diaries are absolutely, part of our lifeblood in a way, because they tell us what somebody was thinking at the time, not what they were fondly remembering in their dotage. And the two things can be quite different. So, I've got very little time, so I'm going to speed through it. But the person is probably someone you've never heard of, Francis Puryear White. This is also what's fantastic. This is a photograph of him taken when the diary was being written. He actually talks about the photograph in the diary. It's the photograph he had taken just before he sat the tripos. He's a student undergraduate at St. John's, become senior wrangler in 1915. The Order of Merit had been discontinued, but he learnt sort of secondhand that he had come top of the tripos, and he basically spends his life in Cambridge. He's a sort of stalwart of the LMS. He's the secretary, the Honour Secretary from 1926, so he's the first editor of the journal of the LMS, which gets founded that year. So what's in the diary? So we learn about the lectures he goes to, lots of details about the things that is going on in the lectures, the lecturers, his reading, his experience of sitting in the tripos, postgraduate funding. And this, of course, is a time before the PhD has come into Britain. And it's really hard to find out how people made that transition from being an undergraduate to a postgraduate, and trying to get pots of money together. So we learn about that. We learn about his friendships, such as with Harold Jeffreys. They were keen cyclists. White lived in Islington, which coincidentally is where I live. And so in the diary, he's describing when he's at home, the streets around where I live. And he cycles regularly from Islington in London to Cambridge, which I found really quite remarkable. The other thing about the diary that was really revealing was that he was a pacifist. And I had no idea until I read this diary of how many mathematicians in Cambridge were pacifists at the time. I mean, much more than if you sort of took the population as a whole. So it was really interesting to kind of unpack all of that. And then we various other things that he's interested in, and of course there's some gossip. So I'm just going to, and then of course we learn about his home life too. And of course, remember, this is during the war, so we hear about things like blackouts and Zeppelin raids and things like that. So as far as lectures are concerned, the main people who feature are Henry Frederick Baker, the geometer, the Lowndean professor, Thomas Bromwich, and Ebenezer Cunningham. Cunningham was also a pacifist, and he's famous for being the person who really introduces relativity theory into Britain. And Larmor, we'll come back to him. As I say, White tells you a lot about what he thinks about these people and their lecturing styles and things, as you'll see. This is just, I mean, to me, this was quite astonishing. This is just the papers and books and things he was reading in the Lent term, just before he does the tripos. And it's a pretty remarkable list. And there was more in leading up to the exams, and there was more in the holidays before. So, you know, Klebsch and Poincaré, Rayleigh, Salmon, Savary, Weber. I mean, it is really, and he tells you what he thinks about them and what is it he's actually doing. This is a bit of gossip. He says when he first hears about Ramanujan appearing in Cambridge, and he says that who apparently invented the integral calculus as a side issue, that his bent lies with the discovery of curious results in various things, but he knows no mathematics. He's about 35, counts differ, he's roughly right there, and he's said to have a wife and numerous children in India. Well, actually, he did have a wife, but he didn't have any children. Tripos exam, so he goes through each of the days of the tripos. I would just point out the fact that on the 7th of June, this was a 6-day exam. They had 4 days in between that part, Schedule A and Schedule B. Beginning of Schedule B, that it was a nasty paper in the afternoon, and because it was so warm, they were allowed to take off their gowns and coats and even to smoke. This was clearly something that was sort of important to White, because at the end of the exam, he celebrates by buying a pipe. And an ounce of Boardman and smokes it, made himself ill, but he did expect it. And then this is a little bit about the funding for White's postgraduate work. The Isaac Newton studentship was something which he does get. What's interesting particularly is he pastes into the diary the testimonials that he gets from Baker and Bromwich of his suitability for the studentship. And we hear about his scholarships and things, but there's a lot about, you know, going to see people, seeing if he can get bits of money here and bits of money there, and he does get the funding for his postgraduate work after doing the tripos in 1915. And this is one of my favourite bits of gossip. He heard an excellent story about Hardy, who'd recently published a Cambridge tract with Marcel Rees, and is awfully bucked at having produced something in collaboration with an enemy in wartime. Rees lives in Denmark, actually, he was wrong there, he lives in Stockholm. Hardy had written to him on some mathematical subject, and the letter contained a good many mathematical symbols, but he mentioned the name of a German worker at the end. The censor got hold of the letter, determined from the German name it must be a code message, spent hours trying to decipher it, and failing altogether, refused to let the letter through. Here, his opinion of Larmor. He doesn't really think much of Larmor. He says he's difficult to follow, frightful to get down in notes. He also mentions here where he's going to the No Conscription Fellowship. This is as part of his pacifist activities. And then a bit later, Larmor's really awful, made several sneering remarks about pure mathematicians, which I'm sure partly for my benefit, and then he quotes what Larmor says. In applied mathematics, one has to feel one's way. Pure mathematicians merely follow their noses. So he doesn't think much of Larmor. And here we have an incident to do with his pacifism. He hears that Hogben, that's Lancelot Hogben, Mathematics for the Million, was a very popular mathematics book published in Britain, where probably most people, they know him for mathematics, is concerned. And then a detective had called for him, and so he went to go to Hogben's rooms, but he wasn't there. And then apparently Hogben then read a paper to the Socialist Society at Newnham and then was arrested, and bail was refused. And later on that day, White goes round to Russell's, and a large number of people turned up, and he mentions the fact that Russell was going to be prosecuted for writing a No Conscription Fellowship leaflet, of which he had acknowledged authorship in the Times. And this was a very famous kind of affair with Russell and him, it ending up with him being expelled from Trinity for that period, and Hardy writes a book about it much later, and so on. So it was really interesting to hear the kind of first-hand thing about it. I think that's... Oh, and then this is White himself comes up in front of tribunals, because of course conscriptions come in, and it gets the net gets wider and wider with conscription. He goes up in front of a couple, and then they get delayed and so on. And then this is the final one, and he's very surprised when he's actually granted exemption from military service, but on the condition he's employed by the Friends Ambulance Service, which is a Quaker organisation, which is what he does. But again, he helpfully pastes into the diary the newspaper cuttings, the local newspaper cuttings. And in this one, he says, the military rep said he'd raised no objection to his exemption, saying he's not as rabid as some of them. And he replied to the military rep, I think I am. He felt he was rabid in his beliefs in pacifism. So that's a very quick run through, but there's a huge amount of information in this diary. As I say, it's a really valuable document for understanding what life was like for a Cambridge student. And also the repetition is useful because you really see what a student's day was like, and how it was formed, and also what he did in the vacations as well. Okay, so now a completely different document. This is also from a Cambridge archive, but it's from the other Cambridge, from Harvard. This is from the papers of Birkhoff. And this is a totally different prospect, because here, instead of 6 boxes, which are quite small and easy to kind of navigate, this is 25 document boxes plus a whole lot of other stuff. And the document boxes are just full of a lot of very thin letters, because Birkhoff kept, very helpfully, he kept all the copies of all his letters going out, as well as the letters coming in. And of course, that was all on that sort of like carbon, really paper, very, very thin paper. And it's, you just get glazed when you see. So actually finding what you want is quite a challenge. But one of the things in the archive is this paper, Some Unsolved Problems of Theoretical Dynamics, which is typed and handwritten manuscript. And this is what interested me, because I'd worked previously on work of Poincaré, and Birkhoff it was actually described as the Poincaré of America. Poincaré was really his hero. And Birkhoff was one of the first generations of American mathematicians to be educated solely in the US. Prior to that, if you were determined to make a mathematical career, the generations before would go to Germany, for example, to do a PhD and so on. He rises to prominence in 1912 with his proof of Poincaré's last theorem, makes his career at Harvard, And for the purposes of my interest in this paper, his Colloquia and lectures of 1920, which get published in 1927, are very important. Of course, he's well known for his ergodic theorem, and from his collected works, we see he published 32 papers on dynamics. He had 45 PhD students in a variety of topics, but the collected works are a really useful resource for all kinds of bits of information. So what about this paper? Well, it comes about because he gave a lecture at the University of Chicago in 1941 for the 50th birthday celebrations. And a summary of it gets published in Science shortly afterwards, but it's just a 2.5-page summary. And he leaves this unpublished manuscript. And in the archives, you see that he writes to the Moscow, he promised the manuscript to the Moscow Mathematical Society, but he'd said to them, look, I'm sorry, I'm not going to send it to you until the hostilities are finished. And of course, he dies in 1944. So that's why it's in the archive unpublished. And I've spoken about the sort of all this background to the manuscript at the last ICM, and you can read about that in the ICM proceedings. So I kind of left the project at the end of my sort of ICM talk was, okay, I know about the background, I know what the problems are, I've transcribed the manuscript. Now I want to try and find out what happened to these problems. Was Birkhoff on the right track? Had anybody solved them? Because, of course, the only thing anybody would know was the paper in Science, which was only 2.5 pages, and this manuscript is about 50 pages altogether. And this was difficult. I showed it to a few mathematicians who sort of looked at it in horror and said, yes, this maths is, we're not sure what's going on here. And it sort of sat with me for a while. And then coming here was the perfect opportunity. I had the chance to get together with some mathematicians to really start and look at this manuscript and really try and understand these problems and what had happened to them. So that is what one of the things I've been working on when I've been here. I also would point out this quote from Gottschalk about Birkhoff not being exactly the clearest person to follow, not being the world's best expositor. So my resources for doing this were mainly 3 fantastic colleagues who've come together to help me, Andy Burbanks from Portsmouth, Dan Russ from the Open University, and Reem Musawi from Queen Mary. And we've been trawling mass SciNet, Central Black, Google Scholar. It's amazing how different things come up in different places. I had a mass of Birkhoff correspondence, which I'd photographed, but I needed to really go through. His dynamical systems in English and in Russian, because there's extra material in that. And looking at later works by other mathematicians. This is a quick little thing about 1 or 2 bits of correspondence. Carichiato's letters have proved very useful. Kakutani, a past PhD student of Birkhoff's, Eric O'Connor, and Stanislas Ulam. And there are others. So this is just to give a quick flavour. And this is our beginning sort of list of the publications that we've kind of been from our searches in the various repositories, sort of archive, Google and mass SciNet and everything. So these are the ones we started to consult. We have to be consulted, and this is not exhaustive. These are the only ones I could really get on the page, just to give you a sense of the sorts of things. And then this is to show you what we're dealing with. So this is the manuscript, and then beside it there we've got the science article. So that is what people would have seen. And of course, remember, this was published during the Second World War, and it was in Science. So it's not in a maths journal, and it's at a time when most people's attentions are elsewhere. So we have found people referring to it, but perhaps not as many as you would like. And of course, Science is a popular journal, so the way the problems have been described is not precise. So actually trying to pull out of the Science article exactly what Birkhoff was talking about is quite difficult. And so this is just an example of the sort of thing we've started to find. So from a paper of Gottschalk's, we found him referring to the science article and showing that he's been able to rephrase this conjecture of Birkhoff, but it also highlights one of the difficulties with it is the terminology that Birkhoff uses is not the sort of terminology that people use today, and there've been kind of various incarnations along the way. So that has been one of the things we've discussed a lot. Problem 12 is one we know, and actually I did know, had been solved in the positive by Meyer, a Russian mathematician, who did it in 1947. But this leads also to other questions, as I've put on the bottom of the slide here, whether it led to, Meyer's paper led to further developments. Problem 13, that we found that, in fact, it's really solved as a consequence, as a corollary of the Helmholtz von Neumann conjecture. And as I say, we can see the comments here on the side. And also to show you the kinds of the sort of manuscript and so on. And finally, problems 14 and 15. And this is where we've actually found, I was contacted by a French mathematician, Bergische, who'd seen my paper, my ICM paper, and wrote to tell me that he had actually solved these problems 14 and 15. Again, these problems in the science article, you can see the short amount of text, but actually in the manuscript, we've got sort of 3 pages of typed text and handwritten notes and things in between where Birkhoff is explaining things rather more substantially. And that is it. Sorry, that was a real kind of rush through, but just to tell you the kinds of things that I do as a historian of maths and how I love being in archives.
To the Isaac Newton Institute and for inviting me here. It's a great honor, great experience to be here. And I will be presenting this project for an online edition of Newton's Principia. So what's the project about? It is part of a larger project, which is the Newton project, which was founded more than 25 years ago by Rob Iliff, who is there, and Scott Mandelbrot. The purpose of this project is to transcribe all the works by Newton, manuscript and printed. And so far, I mean, Newton left a huge archive, a very huge archive. And so far, I think that the Newton project transcribes more than 10 million words. And the Newton project is related. Okay, there is a parent, smaller project in Nova Scotia led by Stephen Snowden. There is a project led by Bill Newman in Bloomington, Indiana, in which the alchemical papers by Newton are transcribed. And what is left to be done is nothing less but the Principia, actually. I should mention also the Cambridge Digital Library, which has digitized all the Newton manuscripts that they hold. Many very interesting manuscripts. Most of the manuscripts related to the Principia are in the University library. And what happens now is that you can leaf through Newton's manuscript and see the transcription provided by the Newton project. So on the left, you have the Cambridge Digital Library. You can download the image, you can compare the images, you can search in the texts that have been transcribed by the Newton projects, you see. So, the Principia has not been yet done. And I remind you that we have 3 editions of the Principia. In the first edition in 1687, 1713, and 1726. Now, it is very interesting what we can do, because we can transcribe and study in detail the manuscripts leading to these three editions. Newton, especially in between the first and the second edition, Newton rethought the Principia very deeply with the help of some of his collaborators, and as we will see later. So, we have printed editions of we have interesting studies by great Newtonian scholars such as Bernard Cohen, who in 1971 wrote for CUP an important introduction to Newton's Principia, where some of this material is studied. But Bernard Cohen could not transcribe all the manuscripts. I mean, it is impossible to do it in a printed edition, as he declares it very clearly. While if this project comes to reality, we will be able to transcribe everything, actually, everything which is left. Then there is an edition of with variants of the three editions of the Principia. Again, it is something that is difficult to use. I think that the digital edition of the Principia will be much easier to navigate. And then there is Tom Whiteside, who in volume 6 of his beautiful edition of the mathematical papers produced an edition of a small selection of the papers that we will consider in a moment. So the texts, a very quick introduction to the texts. Here we see, this is in the Cambridge University Library, we see a draft of the De Motu Corporum in G-room, I say in G-room, you might want to say. Yes. And this is, the beginning of the Principia, if you like. It is a short manuscript that Newton wrote, as we know, as many of us know, because he was visited by Edmund Halley in August 1684 and asked a question about how planets move around the sun if the force is inverse square. Or did Halley ask him a different question? We don't know. So in this manuscript we find a geometric proof that Kepler's area law is valid only if and only if the force is central. And this demonstration, I think, is familiar to most of you because it is reproduced in many introductions to Newtonian mechanics. It is a very, very simple, if you like, proof that for a central force field there is a conservation of angular momentum, as we would say nowadays. And Newton thinks about a body which moves in void, and there is an impulsive force that acts at equal intervals of time and deflects the body, and it is easy to prove that the areas of these triangles are equal one to the other. And then Newton considers a limiting case in which the force acts, he takes the limits and obtains a smooth curve and a continuous force acting on the body. Then Newton has a geometric measure of central force. He thinks about a body which is moving, attracted by a central force, directed towards S. If this force didn't act, the body would move in a straight line at constant speed, but the force is acting, and so the body is deflected, and RQ is a small fall, which, if Q is close to P enough, this fall is in a constant force field, let's say so. And so this little fall from inertial motion, this little deviation from inertial motion is proportional to the force times the square of the time. But the time is proportional to the area spanned by the radius vector which is equal to SP time QT. Because this little focal sector is very much a triangle when Q tends to P. And so Newton obtains a geometric measure of force. And then he proves that if this curve is an ellipse and the body is attracted towards a focus of the ellipse, then the force is inverse square. So if the body moves along an ellipse and the area law is valid for a focus, then the force is inverse square. All this is done geometrically. Now, we have elaborations of the de motu corporum. This is in the hand of Newton's amanuensis. And you see that here Newton introduces some corrections. He has four hypotheses, and he names them laws, lex. So this is the beginning of Newton's idea that dynamics, as we say, using Leibnizian terminology, can be based upon laws. And then we have, Newton's another elaboration of this with many corrections, as you can see. So it's very interesting to follow Newton in his, steps towards publishing the Principia. And this is the copy that was sent to the printer with corrections. Now, in the University Library, there are also copies of the first and the second edition of the Principia with Newton's annotations. Some of these annotations are very long. Newton wanted to change the Principia when he thought about a second edition of the Principia. And here, for example, we see him correcting the data about the orbital radii of Jupiter's four main satellites, and in a facing place, he is adding data about Saturn, you see. So in correcting the Principia, in preparing the Principia for the second edition, Newton was helped by several people. One is this Genevan, Niccolo Fazio de Duillier, who wrote notes to the Principia that related to his attempt to be an editor of the second edition of the Principia. We have David Gregory, Savilian professor of astronomy, a Scottish mathematician who moved to Oxford. And David Gregory wrote a line-by-line commentary of the first edition of the Principia, which is now at the Royal Society. And you can see that, he puts, in square brackets, a little, some words from the Principia, and then he comments on them. It's very interesting. Now, Newton's methods are known to be geometrical, right? We have seen some of his geometrical reasonings before. And this style of Newton was very much praised. For example, the scientist, historian, and philosopher of science, William Whewell, writes, "The ponderous instrument of synthesis, that is geometry, so effective in Newton's hands, has never since been grasped by one who could use it for such purposes, and we gaze at it with admiring curiosity as on some gigantic implement of war, which stands idle among the memorials of ancient days, and makes us wonder what manner of man he was who could wield as a weapon what we can hardly lift as a burden." So this quotation is also meant to raise a bit the level of English, because the Victorian English of Whewell is really beautiful compared to my broken English, I'm afraid. And this is Newton. I mean, Newton lost no chance to praise the methods of the ancients. This is a quotation. To be sure, the ancients' method is more elegant by far than the Cartesian one, for he, Descartes, achieved his results by an algebraic calculus which when transposed into words, following the practice of the ancients, would prove to be so tedious and entangled as to provoke nausea, nor might it be understood. But they accomplished it by certain simple propositions, judging that nothing written in a different style was worthy to be read, and in consequence they were concealing the analysis by which they found their constructions. So this is just to give you a flavor of how passionate was Newton about the geometrical methods. Yet, and I come to the conclusion now, in some of the annotations to the Principia, Newton sometimes uses the calculus. I mentioned to you Gregory's Note. And, we find in Gregory's Note his annotations to a corollary in the Principia. This corollary has to do with the motion of a body in an inverse cube force field. And in the Principia, Newton gives just the geometrical construction of some spiral trajectories traced in an inverse cube force field. He arrives here and leaves a page blank. He doesn't understand how Newton obtained these constructions, which Newton in the Principia says, as many mathematicians do, if you allow me a criticism, these results follow from a quadrature, an integral, we would say, which being easy enough, I omit for the sake of brevity. You see, this is what you often do. But Newton wrote to Gregory a letter in which he translates the corollary 3, and he translates corollary 3 into algebraic symbols, and we can see it in another manuscript that is clearly a preparation of this letter. You see, Newton says, okay, let the distance from the center of force be x, let the force be inverse cube. You see, the force is a constant divided x to the cube. Therefore, the area under this curve, which represents the intensity force in function of distance from the force center, is this constant divided x squared, and therefore, blah, 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 I obtain that I get the sector, that is to say, the polar angle, if I can square, if I can integrate this formula here, and I obtain the time, if I can square this formula here, where x is the distance from the force center. So, do we have here Newton writing differential equations in polar coordinate for inverse square, inverse cube central force motion, perhaps? So this is one of the questions that these manuscripts elicit, actually. And you see, the complexity of the situation is that we have the printed text, which is geometrical. It is a geometrical construction of two spiral orbits. We have Newton's letter to Gregory that allows Gregory to fill the gap in the Note, which is in a symbolic language. Then we have Leibniz and Johann Bernoulli, who reading the Principia translated the Principia into differential calculus. And then we have the differential equations that we have in our, treatises on Newtonian mechanics. So the project is, I think, interesting. In these last two slides, I have characterized in a caricatural way historians and mathematicians as if we were two different animals in a way. But we share the same interest, I guess. But let's say in this simplified, very simplified way, we can say that historians can use the online edition of the Principia in order to navigate in the complex web of printed and manuscript sources. They can access images, compare images and see transcriptions. They can search information, study and compare images. And let's say mathematicians can, add mathematical comments. I mean, I would like very much to have people like Charles Green, who has translated the Principia recently, to contribute to this project. Provide translations of Newton's geometric and algebraic methods into modern notation, and use some of Newton's demonstrations for teaching purposes, I think. The Principia online edition will allow to broach several questions. For example, why were constructions so important to Newton and his contemporaries? What role did algebra and calculus play in Newton's theory of motion? Why was Newton's approach to calculus communicated privately through the circulation of manuscripts rather than in print? Attempts to answer this question will help us to understand the values that guided Newton's mathematical research, what he wanted to achieve, what methods he used, and how he ranked them, how he related his mathematical work to that of ancient models. And this will allow us also to study the reception of the Principia, how the Principia was transformed into something that was different from what Newton actually conceived when he wrote them. It is important to emphasize that the online edition should be carried out taking into account the equally important approaches of both mathematicians and historians, but I think, both mathematicians and historians in this room, I think, that you share my interest, and I'm very interested in your competence, actually. We will be interested in translating Newton's proof into modern notation and checking their validity, as we have suggested in one of the slides, and as Chandrasekhar has done in his commentary, and Green in his recent annotated translations of the Principia. And as I said, mathematicians may also be interested in using some of the material in the online edition for teaching purposes. So thank you very much for your attention.
Okay, I want to touch on 3 projects to illustrate different approaches to the history of 20th century mathematics. And one point I want to stress, and that is a point that both June and Niccolo already made, so you could go home and maybe. The point is that they require various degrees of cooperation between history of mathematics and mathematics. And the 3 projects are the following. First, political crisis and disciplinary development, mathematics in Germany, 1920 to 1960, which I'm working on together with a sociologist of science. Then the Oberwolfach Research Institute for Mathematics, 1944 to 1963, from National Institute for Mathematics, Reichsinstitut für Mathematik, to an international social infrastructure for research, that's the quotation, together with a historian of mathematics, Maria Remenyi. And the third one is Big Mathematics, the classification of finite simple groups, 1950s to 1980, together with Rebecca Waldecker, who is there. And this project brought us to the INI. I begin with the first one, political crisis and disciplinary development. This had 2 points of departure for me. First is a general interest in mathematical research in Germany important to the war effort, talking about World War I. So the question of who did what, when, where, and with whom. Yes, did I say World War I? I mean World War II, of course. So who did what in World War II? And this reaches back to discussions Norbert Schappacher and Moritz Eppler and I had back in 2010. So this was long in the making. And the second is a broader interest in the impact of political crisis on development in mathematics in general. The project focuses on the history of mathematics in Germany between 1920 and 1960, a period characterized by political crisis. You know it, we have the Weimar period, and from 33 to 45 we have the Nazi period, and then we have the post-war period. So that's basically 3 periods of crisis. And we aim at a detailed mapping of mathematics within the German university system from a combined perspective of history of mathematics, history of science, and sociology of science. And the project will offer answers to the questions of who has worked when, on what, in cooperation with whom, in specific research fields. So we really want to map out the research communities and the development of the research communities. We will test several hypotheses, including that during the Nazi period, abstract fields of mathematics were substituted with war-related fields, and more applied fields were supported with funding. In addition, we will examine whether military patronage during the Cold War has led to a focus on particular research fields within mathematics. And in methodological terms, the project connects an archive-based prosopographical approach with bibliometric analysis. So that's where the sociology of science comes in here. And this will allow us to systematically map the historical and institutional development of mathematics in Germany, including specific subdisciplines. Let me say a few words about this approach we have. Our sample includes mathematicians in Germany who either held a professorship or had their habilitation in this period between 1920 and 1960 in Germany, and we realized that Germany is a somewhat unstable unit in this period, naturally. This group, this is a group of approximately 750 persons, and we have collected professional data about them, mainly from university archives based on a questionnaire, which I won't show you. It's a questionnaire with 23 questions, and I just give you some samples. So we ask about the PhD, supervisors, when and where, title, of course, the habilitation, professional data, academic positions, especially where did they work during World War II. That is a black box, really. International contacts, funding, etc., etc. So that's what we try to have in this questionnaire. And that's the data we then want to combine with the publication data in ZB math. And that will allow for we think that will allow for a quite good mapping of the German mathematical community in that period of time. Where do we stand? The data is collected almost, so the next steps will be cleaning the data and combining it with the ZB math data, and then, start the analysis. What has really happened? How has mathematics evolved in Germany between 1920 and 1960? Cooperation here is with sociology of science, as I said, and this is a project where mathematical expertise is helpful but not mandatory. So you could give that to not really everybody, but it's a project where you don't need to be a mathematician to get results. So let us move on to the second example, the Oberwolfach Research Institute for Mathematics, the early period 1944 to 63. The point of departure here is my interest in the history of mathematics in the Nazi period. So we are all familiar with Oberwolfach as being an internationally highly renowned research center. It was founded in late 1944 by Freiburg mathematician Wilhelm Süß as a national institute for mathematics with a wide but rather standard range of responsibilities, and at the time mainly geared towards research related to the war effort. So mathematical problems coming up in rocket design, etc. In the 1950s and 60s, the institute developed into an increasingly international conference center. So what has happened? My interest here is in this understanding just how Oberwolfach as an institution transformed from a projected national institute for mathematics into an international social infrastructure for mathematical research, exclusively hosting conferences. This was a completely new thing in the framework of German academia and beyond. And the extent of Oberwolfach's historical impact on mathematical research in Germany and beyond is an open question, I think. The Institute's history has 4 phases that I will not go into here now. Just let me point you to the Oberwolfach Digital Archive. But really, just after dinner or so, spend half an hour there. It's got PDFs of the abstract books and of the guest books. It's an invaluable resource. Well, they could try to move it into the 21st century. It's 15 years old. That the material is very rich in there. So I do approach the history of the Oberwolfach Institute from 2 perspectives. The first perspective being the institutional development, with a focus on the influence of a political motivated cooperation in the French occupation zone on the development of the MFO and mathematics in Germany. So the example here being the close cooperation with French mathematicians and the influence of Bourbaki coming through Oberwolfach into Germany, especially in the French occupation zone. And the second focus is on the reshaping of the institutional identity of profile of Oberwolfach, of its developing into a conference center, which is something that really is kind of spectacular in the 1950s, at least for the German context. So that needs to be looked into, I think. And the second perspective, of course, is closely related to this. What about mathematics in Oberwolfach? So what is the impact of the Institute on the discipline in general and on specific subdisciplines in Germany? So, and what is the importance for the re-internationalization of mathematics in Germany after 1945? It was pretty isolated. And finally, what is the impact of this developing and newly shaped workshop activities of the Institute in Oberwolfach on mathematics in Germany? And that is pretty difficult to assess, and we have tried to do that by means of studying the history of the workshop series they have in Oberwolfach. Most of you will know that they had these old series in geometry, in history of mathematics, in, in statistics, geometry, group theory, topology. So we have been putting together, with the help of many colleagues, a volume that will hopefully be published this year on the history of these early meetings in Oberwolfach. So wait for it, you will see it in Oberwolfach, and it will be online at the Institute later this year. And from this, it seems clear that the Oberwolfach Institute and the new structure of mathematical work it facilitated, working through conferences, through specific meetings, had an important impact on specific subdisciplines, such as group theory. Rebecca has written on that, or statistics. That was quite surprising for us to see. Helmut Kneser, who was co-director of the Institute, commented on the importance of the MFO with respect to the changing working and communication structure in mathematics in 1960. And this is from a comment he made in the context of the attempts of turning the Oberwolfach Institute into a Max Planck Institute, the failed attempt in the around 1960. And well, here he makes the case for the special mission of Oberwolfach. Given the change of structure that has unfolded in mathematics, new theories and results are found and developed so quickly in the centers of research that mathematicians who only learn of them by printed media cannot take an active part in the research process. It's a problem of communication. Frequent meetings, so meetings in Oberwolfach, between the various research groups are necessary. And then, because of the mobile character of mathematical work, it is possible in mathematics that not only results and methods can be discussed in such meetings, but real research can be done. So that is the case he makes for Oberwolfach. And so that is something that I found really interesting, this role of Oberwolfach supporting this change of structure in mathematical work. So there's a new structure presented in order to answer to the new structure of work in mathematics. And by way of anecdote, Karl Ludwig Siegel early on commented on this new idea, and he said, well, I've seen that in Princeton, a room full of young people discussing things and nothing comes out of it. So there were people who were very critical of this. So cooperation here is, in this project, sporadic but serious cooperation with mathematicians is necessary, as I've tried to show you with the table of contents of our volume. In particular, with respect to this conference series they have in Oberwolfach. It has not been trivial to secure mathematical expertise from various fields, and there are some blanks, and we are aware of that. Complex analysis is still missing, number theory is still missing. So, but the invitation is there, and the material is there as well. Now let's turn to the third project jointly done with Rebecca Waldecker, Big Mathematics, the classification of finite simple groups from the 1950s to 1980. The points of departure for me are an interest in changing ways of doing mathematics in the 20th century and the contexts feeding into these developments. So what are the influences that, well, make mathematics into something different? And the other interest is interest in the history of the classification as such. Our project has two phases. We are in phase one now, which is fun, covering 2 years, and this has a specific focus on securing relevant material. Relevant material meaning doing interviews with major players, that's what Rebecca is doing. Securing written material, correspondence, etc., and consulting material in archives. We went to Chicago, Austin, and Princeton last September. And in phase two, which will definitely take longer than 2 years, we aim at systematically analyzing the history of classification of the finite simple groups, and we will strive to produce an integrated history of the classification project, covering both the evolving of the proof and the various contexts related to the process. And well, this is a black box. We don't yet know how we are going to present this. It won't be a standard monograph, but we'll have a few more days to discuss that here. So let me say a few words about the classification project. The idea to classify finite simple groups is to have a list of building blocks of finite groups, goes back to the late 19th century to Otto Hölder. He's a point of reference here. And work on the classification project reached its peak between 1950 or the 1950s and 1980. And that's the result, the way Aschbacher presented it in 2001. The classification theorem is a highlight of 20th century mathematics, both with respect to its mathematical content, but also to the complex process of proving the result. The original proof is estimated to be spread on somewhere between 10 and 15,000 journal pages, 500 articles written by perhaps 100 or even more mathematicians. So this is a huge amount of, well, material and person power in there. The nature and scope of this enterprise from the 1950s until the 1980s seems quite unprecedented. Therefore, from a historical perspective, the history of the classification offers an excellent opportunity to focus on more general developments in the history of 20th century mathematics, such as changing perceptions of what a mathematical proof may be, So think of the use of computers, think of the complexity or the surveyability of a problem or the unsurveyability of a problem. The character and the many contexts of mathematics as an intergenerational and international collaborative enterprise. Here, think about the role of German emigre mathematicians such as Richard Brouwer and Reinhold Baer in the classification project, or about the roles that trust and consensus play within this enterprise. Then there's the role of Cold War science or Cold War mathematics. That is a hot topic in history of science, Cold War science, and it's coming in history of mathematics, I think. The history of the classification can be studied as a key example, I think, of the impact of politics on research in pure mathematics in the Cold War, namely via new possibilities of funding research in general and mathematical research in particular. And that's a largely unexplored territory and crucial, I think, for the classification project. And then big mathematics, which we have in the title. In 2005, E. Ryan Davis characterized the classification project as industrial scale pure mathematics. And in view of similar assessments, we consider the classification as possibly the first instance of what we tentatively call big mathematics in this project, in a sense adapted from characterizations of big science in the history of science and technology community. So analyzing large projects such as the Large Hadron Colliders or similar things. So let me say a few words about big mathematics, or what it would mean. A big mathematics project would have to be a geographically widespread, teamwork-oriented, resource-intensive project relying on large equipment and at some point necessitating a central strategy and coordination. So that's copy-paste from big science in a way. And we now feel that we can tick off all these boxes for the classification project. It was geographically widespread, mainly in the US, the UK, and Germany. It was teamwork-oriented. It was a resource-intensive project enabled by funding through the National Science Foundation, military agencies, and private foundations such as ESSO or Ford. It relied on large equipment such as powerful computing facilities, and there was a central strategy and coordination, Daniel Gorenstein being described as chief executive officer or coach of the team, or you name it, he was it in a way. And from this starting points, we will further think about whether big mathematics might be a useful concept in our project. And to test this, in the second phase of our project, a close historical analysis of these 5 aspects will be key. In the first phase, the one we are still in, one aspect of special interest is the role of Gorenstein as CEO and the identification of the extent and structure of the network that drove this classification project, really. We wish to reconstruct Gorenstein's exact role and to understand why he was respected as a key authority trusted by the classification community at his time. And this is closely linked to the question of how the group theoretic community came to believe that the proof was near, that is, that the classification result was widely socially accepted, even though there were a few critical voices, the most prominent being that of Jean-Pierre Serre. This brings me back to our long-term goal, an integrated history of the classification project, and that is only possible through the close cooperation of history of mathematics in my person and mathematics group theory in the person of Rebecca. And this is what brought us here, and we already immediately profited from our stay, and we want to thank the INI for having us. So in concluding, I want to come back to the three forms of cooperation I tried to illustrate. The first is a project where no formal cooperation with mathematicians is necessary. I work with a sociologist of science. The second is a project where sporadic but serious cooperation with mathematicians is mandatory. And the third is a project that only works in close cooperation between mathematics and history of mathematics, or history of science. I really want to make the strong point that history of mathematics is part of history of science. And as we have seen, these three forms of cooperation allow for a variety of methodological approaches to the history of the 20th century mathematics, what one might call a sociological approach, studying a whole national community, the German mathematical community in this case, an institutional approach, analyzing a specific institution and its role and impact, and a mathematical approach studying a specific field of mathematics, the classification community. And all of these approaches and others as well are, in my view, necessary to better understand the history of 20th century mathematics, and they require various degrees of cooperation between historians of mathematics and mathematicians. So if you wish, I want to, take this as an open invitation, and I'm sure that's what June and Niccolo argued as well, to cooperate in projects in the history of modern mathematics. Thank you.
Into the room and ask. Yes, please go ahead.
Sorry, I'll come a little bit to the front because I can't speak very well right now. I wondered about your opinion on the role of history among mathematicians. Let me illustrate that a little bit. Sorry, I don't want it to get long, but if you consider a subject like philosophy, I think history of philosophy is almost inextricable from philosophy itself. So contemporary philosophers now discuss endlessly what exactly Kant may have meant or Leibniz may have meant, and that's part of research in philosophy. That's certainly not true in mathematics. Some mathematicians are interested in history, and they often get it wrong, of course, but nonetheless, some of them are interested in history, but nobody is exactly interested in exactly what Newton meant, or exactly what Gauss meant, and so forth. Sometimes it has some curiosity. Some people are curious about it in various ways, but people don't think it's really part of their research. Now, I wonder if you have some thoughts about this, whether it should be like this, or whether it's not like that, whatever thoughts you have. It'd be interesting.
Big question. With,
Well, I'll just press forward. Rebecca and I, she's gone now. We presented our project in Princeton in September. And when they invited us, they told us they would have a panel discussion. And I said, well, I agree to that on one condition. We will not discuss why mathematicians should be interested in history of mathematics. That's, your job. For me, it's something that I offer in a way. And I could give you many arguments why history of mathematics is valuable for math or math teaching. But I feel that I'm in the wrong box in a way as a person to answer that question.
yeah, I may, maybe we go in this way. I may just observe that in the philosophy community, there are many analytic philosophers who practice philosophy in the analytic tradition, who claim that history of philosophy might be pretty useless for them. I mean, we have philosophical problems, we have to solve them, and we solve them better than Descartes. I mean, why should we read the Leibniz or Descartes? I mean, we have progressed now, and we have to go ahead. And you know, this contrast that you describe is not present only in the mathematics community, is present also in the philosophy community.
Yes, but certainly to a very different degree.
Yeah, it is true. I think that you are right, in a different degree. In the same time, I think that history gives a sense of the contingency of the present, in a way. I mean, it gives you an image of the development of mathematics that makes you appreciate that the problems that you are asking yourself now are the result of history that might have gone in a different way. And this, relativity to the context, in a way, that does not deprive mathematics from its epistemic status of a certain form of knowledge. But this awareness of the contingency of the development of mathematics, not only in time, but also geographically. The fact that in different cultures, different mathematical traditions were developed, I think contributes to the formation, the cultural formation of a scientist or a mathematician, I think.
Yeah, I mean, I would certainly endorse what Niccolo says, and I think, but I also think that actually looking back at what mathematicians have done in the past, maybe whether specific to your own discipline or not, is a way of maybe giving yourself ideas for how you can go forward in the future. And I think one thing that we're not discussing here is the role of history in the teaching of mathematics, and the way that it can be used to stimulate mathematical thought in a variety of different environments. And going back to Niccolo's point about the different cultural contexts, I think is enormously valuable, and in helping to raise awareness of the different people at different times and places who contributed to the mathematics that we now have globally, is very important. And the fact that people can also see role models from the past whom they can identify with, and that, and actually for people seeing that mathematics is, it is a human endeavor. We're all human beings here. It's something that, seeing mathematicians struggling in the past and making mistakes and coming, that we can learn from that at whatever stage of mathematical development we're in. So.
No, thank you. I hope the question wasn't too provocative.
No.
So, Karine, you had...
Yes. I have many questions, but I will not ask them all to begin with. But thank you very much to the three of us, because you have given a really very broad idea of what different kinds of historians are doing. Perhaps I begin with a remark about June's talk and Volker's talk. In fact, it was very striking to see Birkhoff's connections with Soviet Union. His book being translated, it was apparently someone from USSR who referred to him as the Poincaré and so on. So I wanted to hear a bit more about this connection. And much later, Oberwolfach has also become a place where East and West were attempted to connect and so on. So it seems to me it should be towards the end of your period, perhaps it's later. So you have not at all touched upon this dimension, which is also a political dimension of the place. So I wanted to know whether you could add something to this.
Well, let me say something. A really important point, Karine, because Birkhoff, in fact, was invited to go to Russia, to the USSR, and of course the invitation was retracted at the period where, in the late 1930s and so forth, and there was real interest in his work. I mean, in the correspondence, you see, and the fact that he was going to give this paper to the Moscow Mathematical Society, and so that has been actually one of the stumbling blocks for me in this particular project, trying to find in the Russian literature the people who have been working on his ideas. And I mean, I have several examples from this correspondence of people saying how much they admire what he's doing, and that it's a stimulation for them. So and of course, the situation in the USSR is what it makes it, it kind of grinds to a halt, and then of course he dies. But actually trying to look and see what was going on in the USSR after the war, and then of course in the Cold War and so forth. So that is one of the challenges for us, and I think it is a very important aspect of this particular project.
Yeah, and about Wolfach, the project stops in 1963. It had to end somewhere, and that's the point when the institute was stabilized financially. And so I have not really looked systematically in what you described, the extended hand to the east. It is there, and you can find it in the correspondence, but it's terribly complicated, as we all know. Getting visa, getting the money, getting people come to the Black Forest from wherever. So they tried, but they very often failed. In the beginning, there still is this close, or the attempt to have a close cooperation with mathematicians from East Germany, but as we all know, that became increasingly difficult as well. So I realize there's a gap there, but it's beyond the project scope.
Paolo, you had a question as well?
Well, I have a naive question for Niccolo about this project of transcribing Newton's Principia. Isn't this something that artificial intelligence could do efficiently, or
Yes.
humans could?
Yes. Actually, it's a pity that Rob left now, the director of the Newton project. But there are now, yes, indeed, programs that work with artificial intelligence, and they help with great efficiency, with hope, to transcribe. So we plan, if this project will be implemented, to use a software which is known as Transcribus, which works, it seems, well enough, and allows the transcription of the text. Plus, there are several things, I don't know what they are. I use them, but I don't know. I drive the car, but I cannot build the car. But in any case, there is something that is known latent semantic analysis, which is a very intimidating thing, which is applied in the Bloomington, Indiana project on the chemistry of Isaac Newton. And you can, search, okay, it is searchable, the transcription, but you can search in such a way that you can find, you can organize the several manuscripts in terms of similarity, and you can, discover several things that you would not discover otherwise without these tools. But so yes, indeed, artificial intelligence will be something that we are thinking about. Also, Scott Mandelbrot, and I finish here, has a project for studying the watermarks of Newton's manuscripts, and I participated to a research group in which these people who use artificial intelligence are helping Scott in the Newton watermark projects in finding, the watermarks are, if you have a piece of paper and you look through the sky, you see an image. And, it's interesting that we can date manuscripts by using this technique. I participated to this workshop, but I said to Scott, no, you don't have to pay anything. I said to my department, don't pay anything. I pay for that because I am an ignoramus in that, and I was participating to it, but I did not say a word. I was just listening to what they were doing, but, you know, yeah. Yes.
Yeah, I had some questions about actually the history of Cambridge mathematics for June. So I was looking up Francis White. He's not listed actually as a senior wrangler in Wikipedia, and I found a biography of him, of Hodge, which doesn't mention this either. But in any case, I wondered how many students read mathematics in Cambridge at that time. And the second question was these comments of, was it Larmor?
Yes,
disparaging pure mathematicians. So, choosing my words carefully, these were attitudes that persisted in Cambridge for some decades after this. And that was actually very important for mathematics in the UK as a whole. And I wondered when the departments of pure and applied mathematics were created in Cambridge.
I can't answer that question, but referring to the senior wrangler, you're right. I mean, the Order of Merit was abolished in 1907, 1909, depending on which way you look at it. But White knew because one of the examiners had told one of the other students, and that's why he writes it in his diary. He says, Grace told, I can't remember the name of the other student who told him. And of course, again, we're in the First World War, so the number of students aren't as great.
Senior wranglers are listed in Wikipedia.
Yeah.
But he's morally a senior wrangler. He's only morally.
Yeah. I mean, it's because probably nobody else. I mean, it's only because I happen to have read this diary, but because he isn't somebody of distinction. When you look at his obituary, I mean, he's a good servant for the LMS, and actually, his research isn't. In geometry isn't great. I mean, interestingly, he does this paper in applied mathematics while he's just a postgraduate. But so I think nobody would have noticed him. I mean, if you look at the list of students at that time, nobody would know who he is and think, well, I wonder if he was senior wrangler. But I have absolutely. I mean, he would not have written that if it wasn't true. I mean, you read the diary and you see the conversation, he reports on the conversations he has with the other students and so forth, and he's extremely diligent. So I think, that's the answer to that question. And I think you're right. I mean, this sort of, and I think part of it is, of course, I mean, I didn't show the full quote, but he then goes on to say, well, I don't know what Larmor would have made of Baker's research, and of course, he's very much under Baker, who was the Lowndean professor of geometry and astronomy, but was a geometer. So that's where his own inclination lies. But so I think that's. I mean, it's just for me. It's just very interesting. I mean, he writes in quite glowing terms about some of the other lecturers, but Larmor is doesn't fare well.
No, but you had
yeah, this has actually been already said after your question and Niccolo's response. I just wanted to point out that the Newton project here in Cambridge, but I mean the Newton project as a project of an electronic edition is a worldwide example that other projects of similar editions are trying to live up to or compare to and are in exchange with. Like I'm a member of the Bernoulli Euler Commission in Basel, and we are trying to live up to this, and we are far from it right now. But especially what has already been realized by, it's a pity that Rob left already. I mean, publication is the theological manuscripts of Newton, and the way they are presented, it is really marvelous, and everybody is invited to look them up on the internet.
Thank you, Robert. Yeah.
A question for June and one for Niccolo. About Birkhoff's paper, the one that never saw print. Do those results come out later?
But that's exactly what we're working on now, because of the language in which they're written and the fact that you know, the science article sort of lists the problems, but very sketchily. So it you know, it's not like the Hilbert problems. I mean, I personally have a sort of sense in which Birkhoff kind of would have quite liked to have, you know, thought himself as a sort of Hilbert. But anyway, that's another story. But he had spoken on problems before, and in Germany in 1927, in Berlin, and that those were published. So actually, the one that Meyer works on is related to the one of the German problems, and he also speaks on problems again in Paris again. But that all I know about those are that he spoke, because he writes that he has that's what he's done, but that doesn't get published. So this project is actually to try and work out exactly what the Birkhoff problems were when you look at them today, and to see whether A, people have picked up on them from the science article, and B, whether actually, if they didn't, other people solved them anyway because they were in the air. They were that was the way it was going. So that's what we're doing. You know, I mean, this is the beginning of topological dynamics. It's a whole new area. So Birkhoff is coining some of the terminology, and so that is what makes it quite difficult.
Thank you. And for Niccolo, you showed some of the details of Newton working out the case for the inverse cube law. In terms of certain quadratures, I was worried as you were describing this. Are those not elliptic integrals, or is this something that was easy to work out?
It is fortunately easier than that. The time integral is algebraic even, so it's a very simple integral. And the other one can be done by substitution of variable, and you get you are not getting into that. No. It's difficult because there are several cases. I mean, Newton restricts the initial conditions such that the velocity is orthogonal to the radius, and he gets a couple of spiral trajectories that are noted as Cotes spiral, because Cotes was able to extend Newton's result and get all the spiral. And the funny thing is that Newton in section 3 of book 1 considers, a logarithmic spiral, and he proves that if a body moves in a logarithmic spiral so that the area law is valid for the pole of the spiral, then the force is inverse square. And in this corollary, he considers, though, the initial condition in such a way that the logarithmic spiral is not possible, because the initial condition is such that the velocity is orthogonal to the radius vector. And he gets two other spiral trajectories, but but everything can be done by, let's say, elementary integration. You don't get into elliptic integrals in this case. Yes. Please.
I have a question for Volker about, you had a slide with a quote about how the classification project is this massive accumulation of papers and pages in journals, and that even the most capable mathematicians would have difficulty. How does this fit within the project? Is there a byproduct of your project where such an overview of these papers, and how does this get tackled within the project?
So yes, we try to identify the papers related to the project, and we counted 1,200 or so, meaning that that's difficult to cope with. And if you want a shorter proof, I didn't show the image, there is the second generation proof they are still doing now, and it's I think as of now it's 10 volumes plus 2 extra volumes for one of these special cases, so it will be 14 volumes in the end. So there is this digest making it a bit easier, but it will be very difficult to tackle this question of what is the relevant corpus of publications, and well, it's difficult to do that with the standard thing like citation analysis, because some papers nobody cites them, everybody reads them, and everybody quotes them in a way or the result, but there's no formal citation. So that is a challenge, yeah.
Maybe a follow-up question, sorry, related to the first question actually, because that could be, I think, an example of a case where history of mathematics can be of very direct interest for mathematicians, right? Especially with something like this where there was a sense in which we believe it has been done, but we're not sure. So having a group of historians that have the perseverance to go through this and give some answer.
Yeah, you're right. We are receiving very positive signals from the community who really go for the project and are open for discussion and interviews and sending their material, because it really gives rise to so many interesting questions, and that there really is an interaction with mathematicians in this field, which is very interesting. And for me, I mean, I always try, maybe I have another perspective, because I always try to sell history of mathematics to historians or historians of science, and then my message is mathematics matters. So history is a way to convey that message, because as you all know, out there are many people who think, well, mathematics, why do we need that? Who would be interested in mathematics? And well, that's my approach to try to contextualize history of mathematics projects so that I can sell them in a way.
Tatiana?
Thank you. Can I make a comment that relates to your question? So, when you talk about the classification of finite suitable groups, one of the things that this has generated, because there are mathematicians who don't quite believe that everything is there, we are starting a new series, provided funding is approved, called Revisiting Fundamental Results. And this was actually motivated by these, and the goal is to bring, but the point is, okay, this is a very important project, the goal is to bring people. So as I was hearing you and also June into this series, what are we looking for? We're looking for very important problems that are not completely done, that maybe were left because they were very important, you know, people got distracted, or because mathematics went in a different way. And so this is a place where maybe if you pair with the mathematicians that are interested, you could collaborate in a setting like this. And this, in some sense, was what motivated actually Venkatesh and IIS also to hold this thing. And if I may, to the answer you gave to the question, you know, I don't want to answer that question. I think the important thing would have been to ask Ache, for example, what he had in mind. He had proposed the same thing, that we do the same thing at SL Math, and what the mathematicians felt would be important from the historians of mathematics is a history of how the ideas have evolved. And that, to answer the question, and sorry if maybe I shouldn't be through, but one of the goals of that was that knowing how ideas in the past evolved might give us ideas of how they should be evolving now. So it's something that maybe closer collaboration could be very productive.
So, Karin, you still have the second question?
In fact, I wanted to ask question while returning to Min Hyung's question, because it seems to me that there are other interests that may lead collaboration or interest from mathematicians. Volker has spoken of political crisis and its impact on the development of mathematics. Well, this may be useful to think about more present-day problems that we have. So this is another way of interacting between historians and mathematicians, and a completely different question, in my view, that derives from Niccolo's talk is the relationship between the private writing for mathematicians and the publication. So we have an example of a disjunction between the way in which someone writes privately and what this person publishes, but we know that this is all over the place, and this may be something interesting to think about together. So these are completely different venues of joint discussion.
Ulrike.
Yeah, and I think it's a part of this conversation, really. I think maybe one should also think of one aspect could be to understand not just the history of ideas, but the different contribution different people make, because I think we all have some interest in understanding the past of our own subjects, and in context of the IMU, prizes are so important, and we give prizes out because we think people have done wonderful things to their fields, and so on. But I think there's something about, and maybe this is also connected with equality and etc., is understanding really why we think these people were so important, and what exactly their contribution was. Was it just, sometimes it's personalities that is just as important maybe than ideas. And of course, maybe this wasn't exactly what people are asking, especially, I mean, the closest might be the CFSG project, but I think certainly from a mathematical point of view, in the context of acknowledging people, I think that is potentially we should all be interested in the history of mathematics, I guess, that's what I'm saying.
And I think, Enrique, you make a very good point, and because I think if we look at the way different mathematical fields have developed, personalities are really important as to, who gets the jobs where, and more recently, but in the past, what disciplines are raised to the top. What are the, we go back to the 18th century, the kind of questions that are asked in the academies and so forth, and how that's shaped the mathematics that we have. And I mean, in the case of Birkhoff, for instance, he is somebody who, for him, it was really important to be involved in in American mathematics. He wanted to promote mathematics in America. His students, for him, his students were important. Getting his students jobs. People were always writing to him saying, I've got a position here, or I've got a student here. Can you just, he was really, that was a big part of what he did, and that's not for everybody, And so I think it's, it's important with these people we see the contributions that they make, and the way that they're viewed in their time is seen in the context not just of the mathematics that they're doing, but the positions which they hold and the positions of influence which they hold. So I think you're absolutely sort of on the money in a sense with thinking about it in that way. For me, I think it's really important that we see these people in the round, because they are the people who are often being rewarded, and it's not just for the mathematics, because they're the visible people. They're the people doing, and sometimes we see the mathematics kind of rising to the surface later, because it's being done by people who are not in the prestigious institutions. They are out in the periphery and so forth. So I think that is very much part of that's an important part of what we do.
Okay, I think we just had half an hour of questions and answers, and there will be a drink now, and I do not want to. This is too much.
We approve. We approve.
I would really like to thank these three speakers for this very modern and very instructive overview of what is current research in the history of mathematics. It was very interesting. Thank you a lot for all of this.